We have a hypothesis testing question here. Now, I've got to admit, when I was at school, I didn't fully understand hypothesis testing. I learned how to do it, when to accept H naught and so on. But if I had to teach it to somebody, I don't think I could have been fully convincing. Whereas now I think I can be pretty convincing. Okay, I've made videos elsewhere if you want to look up on them that go into more detail. But I'm not saying I'll guarantee to help you fully understand it, but I will try my very best, and I'll talk about it in this question. So, we're told that 20% of plants of a certain type suffer from a fungal disease when grown under normal conditions. Some plants of this type are grown using a new method. You're always doing that with hypothesis testing. You've got some kind of standard thing, and then you're trying something new out or something has changed. A random sample of 250 of these plants is chosen. You always pick a sample to, then compare with, and it's found that 36 suffer from the disease. Test at the 2% significance level whether there is evidence that the new method reduces the proportion of plants which suffer from the disease. Now, the proportion of the plants has reduced for the sample, but that doesn't mean you can then make this make a conclusion that for the whole population it has, which that's what hypothesis testing is kind of about. The more in your sample, the more likely it's kind of going to be. But you have these like strict conditions. We need to be sure, or like at least 98% sure that in fact it's gone, that the new method has reduced it. Right, let's set things up. So the first thing to do is set up our hypotheses, H naught. And that's the probability of a plant getting a certain disease. Now, obviously, that is not a success, but within our binomial distribution, it's our success parameter. The probability of success, or in this case, getting the fungal disease in in normal conditions is 0.2. And what we are testing, we think that this new method is going to reduce that. So we think actually there's an alternative hypothesis that it's gone down. Okay, that's really important, and it's here reduces. That's how you know that it's going to be a one-tailed test rather than that it's just changed. And obviously we're going to be looking to the left rather than to the right. Now, at this point, I always like to just define my random variable, which I'm going to call capital X. Let X be the number of plants in the sample which have the disease. And then we're going to assume our null hypothesis is true. There's some things you have to do for the marks, like you have to define H0, H1. This kind of stuff is actually, in red, is the sort of stuff you don't necessarily have to write down. It's just, I'm teaching you good practice, not just about passing the exam. Okay, so this bit in red actually is kind of optional, but it's good practice. But this bit is going to be crucial. So if H naught is true, then X is actually going to follow a binomial distribution because it meets the criteria for binomial distribution. We've got a fixed number of trials. We've got this probability of success, which is, we're going to assume is the same every time and events are independent and so on. 250 trials, and then we can say it's 0.2. Now we know in reality, we've got that 36 suffer from the disease. So we're going to investigate the probability that that has happened because it might just have happened by chance. Just like when you're rolling a dice, you might happen to roll lots of sixes. It doesn't mean the dice is necessarily biased because chance works that way. So we look at the probability that X is less than or equal to 36, not just 36, because 36 by itself, there's not much chance of it happening. We want to include all those values below it as well. Okay, this is always one of the most trickiest bits to explain. Why do we include that? But you've got to remember, as you take more and more, larger and larger sample, each individual probability becomes smaller and smaller. But when you start adding them up, that's when, you get a sizable probability. So we can't just look at the single value. It's actually 36 and everything below. What is the chance of that happening? And for this, we use our calculator So it's actually probability that x is 0 plus the probability x is 1 plus 2 and so on. And the distribution function can figure that out. Binomial CD. This is I could just use a variable. It's not one of those where I have to work out like um, I have to work out the critical region. Sorry, that's what I was trying to get at. I'm given a value here, 36, so I can just put that in. And n is 250. P is 0.2. So we get 0.01389. And what that is saying is that there is actually, if I write it as a percentage, it's going to be 1.39%. There is a 1.39% that this could have happened if p was equal to 0.2. So very, very small. We wouldn't expect to get this view. And we compare that with the significance level because the significance level is like our threshold for what we accept. So 1.39% is less than 2%. Okay, so it's less likely to have happened than our threshold. And that means we're going to reject H0. By the way, you could have compared the decimals directly. I normally do that. I was just trying to turn it into percentage to help. This is less than 0.02. So we reject, and by the way, all the stuff in blue is essential. Reject H0. I'm just going to put in brackets the probability of the event happening is too small. This is just there to help explain it. Whereas if we'd used a 1% significance level, actually it's above 1%, and we would say actually there's enough of a chance. So it's all about what you compare with. And so, different industries and stuff, different significance levels are typically used for what is acceptable, because we can never be completely sure. Actually, that's kind of the point of this. So reject H naught there, and we just need to give a conclusion now. There is sufficient evidence, give context, sufficient evidence that the new method reduces the proportion of plants which suffer from the disease. Okay, it's quite a lot to write, but it's arguably the most important bit. We've applied the hypothesis test, but what does it actually mean? This is what it means. And so then, we could go on from there, maybe use this new method or conduct further trials. I'm not sure. All right, well done on this question. Hope this is all making sense. Stuff in blue, absolutely vital. Hope you're happy with it.